Bismillah ar-Rahman ar-Rahim. This video is about the convexity of matrix inversion for Hermitian positive definite matrices. We have two matrices, A and B, of size n by n. Both are Hermitian and positive definite. What we want to show is that for lambda, a real number between 0 and 1, the inverse of lambda A plus 1 minus lambda B is less than or equal to in a generalized sense. So this is a generalized inequality. On the right-hand side, we have lambda A inverse plus 1 minus lambda B inverse. This inequality means that if we take the right-hand side minus the left-hand side, we end up with an n by n matrix that is Hermitian and positive semi-definite. In this video, PD is positive definite, PSD is positive semi-definite. How can we prove this result? That matrix inversion is a convex matrix function. The main idea here is to do simultaneous diagonalization of the matrices A and B. So this is the trick. Suppose that A is Hermitian and positive definite. In our case here, B is also Hermitian and positive definite. But let's assume that B is just Hermitian. A is Hermitian and positive definite, and B is just Hermitian, not necessarily positive definite. Because A is Hermitian and positive definite, then I can take A and write it as Q lambda Q Hermitian. Q is a unitary matrix of the eigenvectors of A, and the eigenvalues of A are on the main diagonal of the diagonal matrix big lambda. The eigenvalues of A are real valued and are strictly positive because the matrix is positive definite. This can be written as Q and then lambda to the 1/2, and this means that we will take the positive square root of each positive eigenvalue, and this is lambda 1/2, and then we have Q Hermitian. We can think of Q times lambda to the 1/2 as one matrix T, and so this is T Hermitian. We can write A as T Hermitian, and T is an invertible matrix. T is invertible. This is the reason we have this condition that A is positive definite. If A is positive semi-definite, then one or more eigenvalues are 0, and so this matrix lambda here will not be full rank, and T will be rank deficient. By insisting that matrix A is positive definite, matrix T is an invertible matrix. Let's examine T inverse B and then T inverse Hermitian. Note that T inverse Hermitian, I write it like this. T inverse Hermitian is the Hermitian of the inverse, or it is the inverse of the Hermitian. These two processes commute. If you have a non-singular matrix, you can invert it, then take Hermitian, or take Hermitian and then invert it. You will get the same result written like this. T inverse B, T inverse Hermitian. This matrix is Hermitian. Why is this matrix Hermitian? Because this is T inverse B and then T inverse Hermitian. If you take the Hermitian of this product, then you will have T inverse Hermitian, that's T inverse, and then B Hermitian, which is B because B is a Hermitian matrix, and then T inverse Hermitian. So this is a Hermitian matrix. Because it is Hermitian, then this matrix is diagonalizable. And we can do the same eigendecomposition. We can take T inverse B, T inverse Hermitian, and write it as U D U Hermitian. U is a unitary matrix of eigenvectors. It is unitary. So this means that U Hermitian, U is equal to U Hermitian is equal to identity of size n by n. And D is a diagonal matrix of eigenvalues. Multiply both sides from the left by matrix T. So T inverse is identity, and we have B T inverse Hermitian, and then we have T U D U Hermitian. Multiply both sides from the right by T Hermitian, and so this will be B, and then we have T U D U Hermitian T Hermitian, and this is T U D, and then we have T U Hermitian. Let's call this matrix epsilon. As we can see, matrix B can be written as epsilon, and then D, which is a diagonal matrix, and then epsilon Hermitian. Note that epsilon is this product. Matrix T is an invertible matrix. Matrix U is unitary, so it is non-singular. And TU is a full rank matrix. It is invertible. So epsilon is an invertible matrix. Now we can write down matrix B as epsilon D epsilon Hermitian. What about matrix A? We started by doing the eigendecomposition of A and writing A as T Hermitian. Matrix U appeared when we did the eigendecomposition of T inverse B T inverse Hermitian. Recall that U is a unitary matrix. This means the following. Take matrix A, which is T Hermitian. It won't harm if I insert between T and T Hermitian U and U Hermitian. This is identity because U is a unitary matrix. A is equal to TU, and U Hermitian T Hermitian is TU Hermitian. This TU is the matrix epsilon. B is equal to epsilon D epsilon Hermitian. A is equal to ipsi Hermitian. The conclusion now is that if we start with matrix A, which is Hermitian and positive definite, and matrix B, which is Hermitian, just Hermitian, we can obtain an invertible matrix ipsi so that we can write B as ipsi D ipsi Hermitian, which means that if we multiply B from the left by the inverse of ipsi and from the right by the inverse of ipsi Hermitian, we get ipsi inverse B, ipsi inverse Hermitian. This will be the diagonal matrix, which is D. And if we do the same to A, multiplied from the left and the right like B, we will get ipsi inverse A, ipsi inverse Hermitian is equal to identity. As we can see, matrix ipsi can be used to simultaneously diagonalize matrices A and B. Now the question is, what if matrix B is not just Hermitian? What if it is Hermitian and also positive definite? What if B is Hermitian? Okay, so this was needed in this business of simultaneous diagonalization, and also it is positive definite. Let's see. We started by the eigendecomposition of A, then we took this matrix T and we did eigendecomposition to T inverse B, T inverse Hermitian. This is always diagonalizable as a Hermitian matrix. But what if B is positive definite? If B is positive definite, then this matrix is also positive definite. Matrix B is positive definite. This means that if we take vector Z in Cn and we construct the quadratic form Z Hermitian Bz, this quadratic form is greater than or equal to 0 for every Z and is 0 if and only if Z is the all zero vector. If we want to investigate T inverse B, T inverse Hermitian, we will take vector Y in the n-dimensional space, and then we examine the quadratic form Y Hermitian, T inverse B, T inverse Hermitian Y. Now, T inverse Hermitian Y is an n-dimensional column vector, and this is its Hermitian here. And because B is positive definite, then this quadratic form will also be greater than or equal to 0. And it is 0 if and only if T inverse Hermitian Y is the all zero vector. T is an invertible matrix, and so this is the all zero vector if and only if Y is the all zero vector. So if B is a positive definite matrix, T inverse B, T inverse Hermitian is also positive definite. And the converse is true. If this matrix is known to be positive definite, then this matrix B is positive definite. The reason behind this is that when we have an invertible matrix, the invertible matrix is a bijective map from Cn to Cn. If T inverse B, T inverse is a matrix that is Hermitian and positive definite, then when we do its eigendecomposition, what we will get is a diagonal matrix of eigenvalues, and the eigenvalues are all real valued and strictly positive. So the difference, if B is positive definite, it's not just that D is a diagonal matrix with real eigenvalues on the main diagonal, those eigenvalues will be positive. Thus, if B is Hermitian and positive definite, the main diagonal elements of matrix D, those elements are strictly positive. Simultaneous diagonalization requires only that B is Hermitian. If it's also positive definite, then this matrix is a matrix with strictly positive real numbers on its main diagonal. This is the topic of simultaneous diagonalization. Let's remind ourselves what the main task was. The main task is to show that lambda A inverse plus 1 minus lambda B inverse minus the inverse of lambda A plus 1 minus lambda B, this convex combination of the Hermitian positive definite matrices A and B. We want to show that this is positive semidefinite. We will write down A and B and A inverse and B inverse using matrices ipsi and D. A is ipsi Hermitian. A inverse is ipsi inverse Hermitian ipsi inverse. B is ipsi D ipsi Hermitian, and B inverse is ipsi inverse Hermitian, D inverse ipsi inverse. The matrix that we want to show is positive semidefinite is lambda A inverse plus 1 minus lambda B inverse minus lambda A plus 1 minus lambda B inverse. This is lambda ipsi inverse Hermitian ipsi inverse plus 1 minus lambda ipsi inverse Hermitian D inverse ipsi inverse. This should be inverse. And then we have an inverse here, lambda ipsi Hermitian plus 1 minus lambda ipsi D ipsi Hermitian. Inside the bracket, let's take ipsi as a common factor on the left and ipsi Hermitian as a common factor on the right. Between them, there will be lambda, and then we have identity of size n by n plus 1 minus lambda d. Note that this is a diagonal matrix. Now, if we apply the inverse, then we get ipsi inverse Hermitian, then the inverse of this diagonal matrix, lambda identity plus 1 minus lambda d, and then we have here ipsi inverse. Note that we have ipsi inverse, ipsi inverse, ipsi inverse, ipsi inverse Hermitian, ipsi inverse Hermitian, ipsi inverse Hermitian, and This means that we can take ipsi inverse Hermitian and put it on the left. We can take ipsi inverse and put it on the right, because this is an invertible matrix. If we show that the matrix in between is positive semi-definite, then this full matrix will be positive semi-definite. In this big bracket, we have lambda times identity plus 1 minus lambda, and then we have D inverse, and then we have the inverse of this diagonal matrix, which is lambda I n by n plus 1 minus lambda, and then we have D. Suppose that D is eta 1, eta 2, all the way to eta n. Those are the positive real numbers on the main diagonal. The matrix that we have looks like this. The first element will be lambda times 1 plus 1 minus lambda, and then we have 1 over eta 1, and then we have minus 1 over lambda times 1 plus 1 minus lambda, and then we have D here, so here we have eta 1. Element jj will be lambda plus 1 minus lambda, 1 over eta j minus 1 over lambda plus 1 minus lambda eta j. Checking whether the diagonal matrix is positive semi-definite or positive definite is very easy. The matrix is positive semi-definite if the main diagonal elements are non-negative, and the matrix is positive definite if all the elements on the main diagonal are strictly positive. We have elements that look like this. Claim, excluding the trivial cases of lambda equals 0 or lambda equals 1, element jj is strictly positive unless eta j is equal to 1. Otherwise, element jj is equal to 0. So this means that the elements here on the main diagonal of this diagonal matrix between ipsi inverse Hermitian and ipsi inverse, these are non-negative real numbers, indicating that this matrix is indeed a positive semi-definite matrix, and the full product is also positive semi-definite. And in fact, if there is no eta that is equal to 1 and lambda is strictly between 0 and 1, then actually this matrix will be positive definite. The last thing is to justify this claim here. The reason is the strict convexity of the function g of alpha is equal to 1 over alpha, where alpha is a positive real number. This function is convex. If we differentiate this function, the first derivative is minus 1 over alpha squared, and the second derivative is 2 divided by alpha cubed, which is strictly positive. Because the second derivative is strictly positive on the domain, which is the set of positive real numbers, then this function is strictly convex. If a function is strictly convex, it means that for lambda between 0 and 1, and alpha 1 not equal to alpha 2, a strictly convex function will satisfy the g of lambda alpha 1 plus 1 minus lambda alpha 2 is strictly less than lambda g of alpha 1 plus 1 minus lambda g of alpha 2. We have 1 over lambda alpha 1 plus 1 minus lambda alpha 2. This is strictly less than lambda over alpha 1 plus 1 minus lambda over alpha 2. In our case here, alpha 1 is equal to 1 and alpha 2 is equal to eta j. So as we can see, this quantity is indeed strictly positive. It's only equal to 0 if eta j is equal to 1. To conclude, if matrices A and B are Hermitian and positive definite, then lambda A inverse plus 1 minus lambda B inverse minus the inverse of lambda A plus 1 minus lambda B, where lambda is between 0 and 1, this is a positive semi-definite matrix. Therefore, for Hermitian positive definite matrices, matrix inversion is convex.